All right, welcome to Solution Equilibrium. This is part two. In this one, what I want to do is I want to go ahead and show you how to do some calculations with buffers and pH and that kind of thing. So we learned last time that a buffer is where you take a acid and you then also add to it its conjugate base. So in this case, we have acetic acid and we have sodium acetate. So the acetate is going to end up being an additional conjugate base into the situation. So what we need to do is we need to write out the reaction. So the reaction right here is acetic acid turning into sodium acetate. It's going to look like this. And then the calculation as far as figuring out the pH, what we're going to have to do is set up an ice table because we have an initial amount of acetic acid, right? We have 0.20 molar acetic acid right there. And then we also have an initial amount of the conjugate base. With the common ion effect, when I put sodium acetate into the solution, sodium, of course, doesn't contribute at all. And the acetate will. The acetate is the conjugate base for the acetic acid. So classic buffer situation. It's a similar one that we looked at before. And so here we go. So here's the initial value. So my ice table goes like this. Goes right underneath my balanced equation. And my initial amount is 0.2 molar of that. And then 0.2 molar of that. And 0 of this initially. Of course, what's going to happen is that this is going to be reduced, we know, because a lot of this is going to be dissociated and create the hydronium ion. And then this will be added to. Because this is a product. This will be added to, but not as much of this can be reduced, right? Because this is here and sort of blocking it. So it's actually going to hinder some of the transition of the acetic acid into acetate. All right, so here's our equilibrium expression. So this one is 0.20 minus x, because this is a value of x, because there's a 1 there. And this is 0.10 plus x, because we're going to be adding some amount of molarity to what we have already. All right, so what do we do from here? Well, what we can do is what we've always done with the ice tables is then to put these values, these factors, into our equilibrium constant expression. So here is quite a bit of stuff here I've written out. And so here we have the Ka of acetic acid. So we can look this up. So the Ka of acetic acid is something that you can just look up in the back of the book, right? So the Ka is 1.8 times 10 to the negative fifth. So that means, according to our ice table, because we know that the Ka equals the concentration of the products divided by the concentration of the reactants, 1.5 times 10 to the negative fifth equals, here's my two products. I've got 0.10 plus x, so 0.10 plus x right there, times x, divided by 0.20 minus x, which is this one right here. Now, that's a lot of algebra, and you could do it. But one thing that we've learned is actually that the value of x is very, 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 very small. So adding this little teeny bit right here probably isn't going to affect it too much. And subtracting this same little teeny bit right here probably isn't going to affect that too much. What we really want to know is just this value right here. So actually, as long as our initial amount is not more, if you take your initial amount and you multiply it times you compare that to your Ka multiplied times 100, as long as this that's not more. So 1.8 times 10 to the negative fifth times 100 is nowhere near 0.20. So we're okay. So what we can do is we can actually take away this plus x and take away this minus x. So here's what we get. We get 0.10 times x, so 0.10x divided by 0.20. And actually that's something that you can just use from here on out. So this is to figure out a buffer. So this is what I call my buffer shortcut equation. So not mine, but that's what we use. So Ka is going to equal X times the molarity of the base divided by the molarity of the acid. And so the molarity of our conjugate base was 0.1, so X times 0.1 divided by molarity of our acid, which was 0.20. So let's go ahead and solve that. So when we solve that, we're going to simply multiply by 0.20 and then divide by 0.1, and we get this right here. So then we need to turn that into pH because that was the question. We wanted to know what is the pH of a situation in which we put these two things together. And so what pH does that buffer create? Well, we have a 4.44 buffer, so acidic for sure, because we multiplied that value of X, because remember X equals the hydronium ion concentration. That was what we were solving for right there. And so it equals 4.44. Here's another sort of logarithmic shortcut. So you could just actually solve for the pH all in one kind of fell swoop in your calculator if you'd like. So pH actually equals the pKa plus the log times the molarity of the base divided by the molarity of the acid. So you might be asking, what is pKa? Well, it's just like pH. So it's a logarithmic function of Ka. So we would actually just say that pKa equals the negative log of Ka, just like pH equals the negative log of the hydrogen ion concentration. So you know, you take the negative log of this. That's going to be your pKa for this situation, plus the log of these two divided by each other. So this is kind of a logarithmic shortcut in order to just quickly just solve pH from that. All right, so there you go. So there's one kind of quick buffer situation, and we'll be solving some more of these as we go along with the buffer situations.